Black holes are supermassive objects that have a gravitational pull that is so strong that even light cannot escape from them. Hence the name black holes. Black holes are formed when massive stars reach the end of their life. They have burnt all of their fuel and then start to collapse under the gravitational pull of their own mass. If they are large enough, there will be nothing that can stop this implosion, and they will finally collapse to a singularity, a single point where all the laws of physics break down. Surrounding the black hole singularity, there is a region called the event horizon. Outside the event horizon, light can still escape the gravitational pull of the black hole, but once inside the horizon, there is no escape. Another way of seeing this is to visualize gravity as creating a flow in the fabric of space. Under the effect of the black hole, space flows towards the singularity at an ever-increasing speed as it closes in. All objects, and also light, are dragged along by this flow, just like fish are dragged along by the flow of a river. When the flow becomes faster than the speed of light, then escape becomes impossible, just like fish cannot swim upstream if the water flow is too fast. In the early 70s, Bekenstein and Hawking realized that black holes are actually not completely black. They can emit some light. This light is coming from a very unexpected and remarkable effect. The black hole horizon modifies empty space to the point that it literally rips photons, light particles, out of the vacuum. The reason this effect is so fascinating is because it is a beautifully simple example of the interaction between gravity, here represented by the black hole, and quantum mechanics. Building a model of the universe that combines gravity and quantum mechanics turns out to be very hard and has not been done yet. Quantum mechanics tells us that emptiness, what we call the vacuum, is not truly empty. There is a continuous boiling froth of particles that come and go. These particles always come and go in pairs, another result of quantum mechanics. We cannot directly see this boiling froth because it forms a uniform background, what we call a ground state, and we cannot directly extract energy from it. However, close to an event horizon, every now and again one of the particles from the vacuum pair might fall into the black hole, and the other particle might escape. For a person looking at the black hole from outside, it will appear that the black hole is emitting light. This light is known as Hawking radiation. Unfortunately, this light is also very, very weak, and we have little hope of seeing it using our telescopes. However, in 1981, Bill Unruh proposed to create artificial black hole horizons using flowing water instead of flowing space. His idea may seem naively simple, yet it works beautifully well. The mathematics tells us that the horizon generated by a small waterfall in a flowing medium will actually generate Hawking radiation. Since then, many different systems have been proposed to generate a flowing medium of some kind. We use intense laser pulses with energies that are so large that they strongly affect the space in which they propagate. In a gas, they can guide lightning, sparks of electricity. In a piece of glass, they can create an artificial horizon. Indeed, these pulses of light change the refractive index of the glass. This change occurs very rapidly and remains locked to the moving laser pulse. This in turn creates an effective flowing medium. We may then use our skills in shaping laser pulses to tailor the properties of the horizons we generate. This allows us to then study how different kinds of horizons interact with light and also with a quantum vacuum. We can ask ourselves questions such as, can we generate Hawking radiation? And what does it look like? Can we probe the horizon with another light pulse? What happens to it when it approaches the horizon? And are there any technologies that may use these artificial horizons? These are just some of the questions that we are trying to answer with our research.